Welcome to Math 201 lecture on 2.1 and 2.2, average and instantaneous velocity and the derivative. Suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Fact, the height s of a falling object is given by s of t is equal to 1/2 at squared plus v naught t plus s naught, where a is the acceleration due to gravity, v naught is the initial velocity, and s naught is the initial height. Write a formula for the height of the ball t seconds after it is dropped. So I'm just going to plug in the values that we know here. Okay, so we have s of t. The acceleration due to gravity is negative 9.8. So this is going to be 1/2 times negative 9.8 t squared plus v naught t. Okay, so v naught is the initial velocity. And if you're just dropping an object from the CN tower, so you're just holding it there and you let it go, its initial velocity is 0. Like the moment you let it go, its velocity is 0 because you didn't throw it down with force, you didn't throw it up in the air. So its initial velocity is 0. So we're going to put 0t plus s naught, which is its initial height, which is 450 meters, the height of the tower. So that's going to simplify to negative 4.9 t squared plus 450. Okay, now we want to calculate the average velocity of the ball from t equals 5 to t equals 9. So average velocity is just change in distance over change in time. Okay, and we have a formula for the distance that the ball has traveled, or it tells us the height of the ball. And so if I want to know the change in distance, I'll take the height at 9 seconds, the height at 5 seconds, and subtract them. Okay, so this is going to be s of 9 minus s of 5 over 9 minus 5 being 4 seconds um, total. So we'll just have to use a calculator for this. I've already done that, and it comes out to 53.1 minus 327.5 over 4, which is negative 68.6. And my units here are going to be my distance units over my time units, right? These are measured in meters. S of 9, that is your height in meters. This is a height in meters. S of 5, meters minus meters is meters over 4 seconds. So this is meters per second. Okay. And before we move on, I just want to address the fact that this average velocity is negative. Why would velocity come out negative? Because this object, this ball, is falling. It's going down towards the ground, and velocity is speed, but with a sign that indicates direction. So negative is generally the down direction. So this ball is falling at 68.6 meters per second. The negative indicates that it's going down. Okay, so another thing I'd like you to notice about this calculation, change in distance over change in time, I'm really subtracting the y values on top and I'm subtracting the x values on the bottom. So this is a calculation of slope, right? This is a change in y over a change in x, or because is representing distance and x is representing time, it's change in distance over change in time. But in more general sense, this is just a change in y over a change in x. So this is a slope of the line connecting points on this curve. Okay, so on the next slide, we're going to look at a picture of this curve and look at the line connecting those points. Okay, so here is a graph of the height of the ball as it falls from the CN tower. So this is the formula that we wrote earlier, negative 4.9 t squared plus 450. And what we just calculated was the average velocity from t equals 5 to t equals 9. So I'm going to put on this curve the points 5 comma s of 5 and 9 comma s of 9. Okay, so now you can see that I plotted the points 5 comma s of 5, which is 5 comma 327.5. So that's this point right here. And then 9 comma s of 9. So that's my x and my y. 9 comma 53.1. That's my b. I created a line to connect those 2 points. That's line F here. And then I had GeoGebra calculate its slope, negative 68.6. Okay, we're going to repeat this process with a couple of other points. Okay, so instead of going from 5 to 9, I'm going to make the interval smaller and go from 5 to 6. Okay, so instead of 9 comma s of 9, I'm going to do 6 comma s of 6. I'm just going to change that 1 point. That is 6 comma s of 6. All my other calculations should automatically update. Okay, so my slope comes out to negative 53.9. Let's just keep that in our brains for a minute. We're going to write it down on the next slide, but negative 53.9. And then I'm going to make the interval even smaller. Instead of going from 5 to 6, I'm going to go to 5 to 5.5. Okay, and now my points are even closer together, A and B, right? And the slope is now negative 51.45. If what I'm interested in is the instantaneous velocity of the ball at t equals 5, I could make that point B closer and closer and closer to point A, right? So this point B right here, we started out at 9 comma s of 9, like way over here, and then we moved it closer and closer, and I could move it even closer to get a really, really small time interval to find out how fast that ball was traveling over that really, really small time interval. And the smaller I make that time interval, the closer I'm going to get to the instantaneous velocity of the ball at t equals 5. So let's go ahead and make that interval even smaller. So instead of 5.5, let's make it 5.25. Okay, and now my slope is negative 50.2249. Let's make the interval even smaller. Let's make it 5.1. Okay, and now my slope is negative 49.49000003. Let's make it even smaller. Let's make it 5.01. Teeny tiny time interval from 5 to 5.01. We'll get the average velocity and negative 49.04900003. Okay, so let's go ahead and go to the next slide and record all of the results that we got. Okay, so we calculated the average velocity from 5 to 6, and that came out to negative 53.9. And we did that by calculating the slope between 2 points, 5 comma s of 5 and 6 comma s of 6. So the calculation looks like this. And that comes out to negative 53.9 meters per second. Okay, and then the average velocity of the ball from 5 to 5.5, we calculated the slope of that line. And the calculation that GeoGebra did was 5.5, s of 5.5 minus s of 5 over 5.5 minus 5. And that came out to negative 51.45 meters per second. Okay, and then we made that interval smaller and smaller and smaller. We went from 5 to 5.25, 5 to 5.1, 5 to 5.01. And it seemed like the slope of the line was approaching a particular value. Um, if you don't remember or didn't notice, like just rewind the video a little bit and go watch um, what the slopes were coming out to. And they were getting closer and closer to negative 49 meters per second. And if you want, you can open up a GeoGebra file on your own, do what I did, and make the interval even smaller. So as we just saw, the graphical interpretation of average velocity is the slope of a secant line, right? Which is a line connecting 2 points on a curve. So in our example, we had this curve that looked like this, and we connected 2 points. with a line, and the slope of that line was your average velocity. And then what is the graphical interpretation of instantaneous velocity? Well, graphically, we took this second point and we were moving it closer and closer and closer to the first point. And the moment that they merge, what you're actually looking at is the slope of a tangent line. So I'm going to draw a picture of it, like what we were just doing. This is the point of interest. The instantaneous velocity at that point is the slope of the tangent line. It's when you take a smaller and smaller time interval where you move this point closer and closer and closer to the point at t equals 5, there's a moment where these 2 points merge, right? And then what you're drawing is a tangent line to the curve. All right, so instead of finding a few average velocities and then making our best guess about what the instantaneous velocity is at t equals 5 seconds, we guessed it was -49 based on the values that we had GeoGebra calculate for us. We're going to try to do things a bit more formally and be a bit more sure that the instantaneous velocity is actually -49. So here's a picture of the same graph that we were just using in GeoGebra. So this is the curve -4.9 t squared plus 450. That's the height of the ball. Okay, and then I have a point here, my fixed point, which is 5 comma s of 5 or 5 comma 327 and a half. This is called my fixed point. It's not going to move. And then I have a varying point, okay, another point somewhere to the right. And we are going to label this varying point 5 plus h, comma s of 5 plus h. Okay, so 5 plus h means 5 plus a little bit. So the h is the horizontal distance between the fixed point and the varying point. So I'm going to highlight that from the fixed point to the varying point. That distance is what we're going to call h. So what we did in the previous slide is we calculated the average velocity from the fixed point to the varying point, okay? And we moved that varying point closer and closer and closer to the fixed point. So let me just write down a calculation for the average velocity. So we would do s of 5 plus h minus s of 5 all over 5 plus h minus 5. That's my average velocity, okay, between the fixed point and the varying point. And then I'm going to simplify 5 plus h minus 5. That's just h. So I'm just going to write that as an h. And then what we did is we let that value of h get smaller and smaller and smaller, right? So we let the varying point get closer and closer and closer to the fixed point. So this distance, this horizontal distance between the fixed point and the varying point was shrinking to 0. So if I want the instantaneous velocity, I take the limit as h approaches 0 of the average velocity. And that gives me velocity instantaneous at t equals 5. So let's actually do the calculation. Okay, I want to calculate um, the average velocity between over the time interval 5 to 5 plus h. Okay, so remember my distance formula, my height formula is -4.9 t squared plus 450. So my average velocity from t equals 5 to t equals 5 plus h would be change in distance over change in time. So s of 5 plus h minus s of 5 over 5 plus h minus 5. So s of 5 plus h, this is just function notation. That means in the formula for s, replace the t with a 5 plus h. Everywhere we see a t, replace it with a 5 plus h. So this is going to be -4.9 times 5 plus h squared plus 450 minus s of 5, which we already know, I think it was 327.5. We calculated that a little while back. And if you forgot, you could just put it in a calculator. So 327.5 all over 5 plus h minus 5, which is just h. And now I'm just going to simplify this. I'm not taking a limit or anything. I'm not doing the instantaneous velocity yet. I'm just going to simplify this calculation for average velocity from t equals 5 to some point a little bit in the future, t equals 5 plus h. Okay, so let's see. I'm going to start by squaring this 5 plus h, right? Order of operations says do this exponent first. So this is going to be negative 4.9 times 25 plus 10h plus h squared plus 450 minus 327.5 all over h. Okay, I'm going to distribute this negative 4.9 and I get negative 122.5 minus 49h minus 4.9h squared plus 450 minus 327.5 all over h. Okay, and now I'm going to combine like terms. Okay, so I've got some like terms, negative 122.5 plus 450 minus 327.5. We could put that in a calculator or do it in our heads, and it turns out that those all go away. Those cancel. They add up to 0. So my next line is going to be negative 4.9h squared minus 49h all over h. Okay, and now my numerator, both terms have an h in them, so I can factor out an h, and I have h times negative 4.9h minus 49 all over h. My h's on the top and the bottom cancel. And then my final expression is going to be negative 4.9h minus 49. Okay, so that is a simplified expression that will calculate average velocity from t equals 5 to t equals 5 plus h, some h seconds in the future. Okay, what does this expression represent geometrically in this graph? So I have the fixed point at 5 comma 327.5, and then the varying point, remember this was at 5 plus h comma s of 5 plus h. Okay. And this expression is just a simplified version of calculating the slope between these 2 points. Okay, so it is the slope of this secant line. So my average velocity is the slope of this secant line. To calculate the instantaneous velocity at t equals 5, we let h go to 0. We let the varying point approach the fixed point. We let that distance h between the varying point and the fixed point approach 0. So our final calculation is that the instantaneous velocity at t equals 5 is just the average velocity from 5 to 5 plus h, but then we take a limit as h goes to 0, as the distance between the 2 points goes to 0. So that's the limit as h goes to 0 of negative 49 minus 4.9h, because this is, we already did all the work to simplify this into this. And now I just take the limit. And this is just a line, which is continuous, which means we can use the rule where we can just plug this value in for h. Okay, so this is negative 49 minus 4.9 times 0, which is negative 49 meters per second. So we've confirmed our earlier guess of the limit based on calculations where h started out as 4 and then 1 and then a half and then a quarter and then 0.1 and then 0.01. And it appeared that the average velocities were approaching negative 49. And now we have confirmed it by calculating the limit algebraically. Okay, very important. The instantaneous velocity of the function y equals f of t at t equals a is the limit as h goes to 0 of f of a plus h minus f of a over h. This is a definition, an important definition for the semester. And note that the fraction f of a plus h minus f of a all over h is comes up so frequently that it has a name, and it's called the difference quotient of the function. When we talk about the slope of a curve, we mean the slope of a tangent line for that curve. This activity is the first activity for the lesson. I want you to attempt the activity on your own. So pause this video, work through it on your own, and then come back and watch to confirm your results or get an explanation if you didn't know what to do. Okay, go ahead and pause now. Okay, now that you've tried to go through this activity on your own, um, we'll go through it together. So the tortoise, the hare, and the rhinoceros begin a 9-mile race at t equals 0 hours. Remarkably, a three-way tie results. It takes each competitor exactly 2 hours to finish. The tortoise's style is slow and steady. She runs the entire race without speeding up or slowing down at all. The hare's style is more erratic. He runs half of the race at a constant speed in the first 20 minutes, stops for a long tea, then runs the second half at a constant speed in the last 20 minutes. And the rhino, an amateur mathematician, runs so that her position r of t in miles from the starting line is always exactly 4.5 t to the 3 minus t. Okay, what is the average velocity on the time interval from 0 to 2 of each animal? So we know that each animal finished the race in 2 hours. Okay, it takes each competitor exactly 2 hours to finish. So we want the average velocity of each animal at exactly over the entire race, entire 9-mile race. Okay, so for all of these, velocity average would be change in distance over change in time, and they all ran 9 miles in 2 hours. Okay, so this is 4.5 miles per hour on average for every animal. They all ran an average 4.5 miles per hour for 2 hours. Okay, despite having all ran the same average race, they all ran 9 miles in 2 hours. They had very different styles. Okay, so we want to sketch the position of the tortoise and the hare over time. Okay, so the tortoise was the slow and steady. Okay, so we are doing position, so miles traveled compared to time. So this should be increasing at a steady, constant rate. So as the tortoise runs, right, they start at 0 minutes and 0 miles traveled, and they finish at 2 hours, 9 miles traveled. And there was just a steady increase in distance traveled the whole way. So just a nice speed increase. Now, the hare, on the other hand, ran a very different race. They started at 0, 0 as well, 0 hours, 0 miles, and they finished at 2 hours, 9 miles. But what happened in between was very different. Okay, so over the first 20 minutes, the hare ran very fast. Okay, runs half the race at a constant speed in the first 20 minutes. Half the race is 4.5 miles. So about half the race, which is halfway to 9. And in 20 minutes, so I got to break this first hour into 5 parts. Yeah, so it's 20, 40, 60, 80, 100. Sorry, there's only 3 sets of 20 minutes in an hour because hours are 60 minutes, not 100. Okay, so break this into thirds. Okay, so 20 minutes is a third of an hour. So in the first 20 minutes, they ran half the race. So they got to the 4.5 mile mark. Okay. So fast running from 0 to 20 minutes. Okay. And then they stopped for a long tea, which means they didn't run at all. They were just, their position did not change until the last 20 minutes when they ran the final half of the race. Okay. So until here, the last 20 minutes, they just stayed put, having a nice little tea. Okay. And then in the last 20 minutes, they sprinted to run the second half of the race. Okay. What was the instantaneous velocity of the tortoise at time t equals 1? Why do we not need a limit to find this? Okay, so the tortoise, I'm going to grab their race and paste it in here. Okay, so the instantaneous velocity of the tortoise at time t equals 1. So right here at 1, mark what I'm interested in at this moment here. Okay, is going to be 4.5, which was the speed that the tortoise was running for the entire race. Their speed never changed. So their average speed over the course of the race is also their instantaneous speed at any given moment. Okay, so this is 4.5 miles per hour because they ran a constant velocity. Okay, and what is the instantaneous velocity of the hare at time t equals 1? Well, at time t equals 1, the hare is not moving. They're just sitting there having tea. So we don't need a limit to calculate that instantaneous velocity because it's 0. The hare is not moving. So now we want to set up a difference quotient to estimate the instantaneous velocity of the rhinoceros at time t equals 1. So that's the a value, t equals 1. So the instantaneous velocity, remember, we have a definition for how we calculate instantaneous velocity. It is the limit as h goes to 0 of r of 1 plus h minus r of 1 all over h. So that is the average velocity from t equals 1 to t equals 1 plus h. So h seconds in the future. And this gives you the average velocity, and then you take the limit as h goes to 0 to get instantaneous velocity. Okay, but they actually want us to estimate instantaneous velocity. The best way to estimate instantaneous velocity is with an average velocity with a small time interval. So we're going to say this is approximately equal to r of 1 plus h minus r of 1 all over h when with h small, a small h. So let's make h 0.1. So this is pretty arbitrary, and what small means depends on how good you want your estimate to be. But I'm going to choose h approximately, we're going to have h be 0.1. Okay. So my velocity instantaneous is going to be approximately r of 1.1 minus r of 1 all over 0.1. And then I do have a formula for r of t, so I can calculate r of 1.1 and r of 1. So I just put 1.1 in for all my t's, I put 1 in for all my t's, finish this calculation. So r of 1.1, that's going to be 4.5 times 1.1 to the 3 minus 1.1 minus, if I plug in a 1 for t, I get 4.5. And that's all over 0.1, which comes out to, if we just use a calculator, 9 miles per hour. So the value of the difference quotient does come out to 9 miles per hour approximately. Imagine that you are a radio reporter describing the events as you see them at time t equals 1. Tell your audience the status of the race. For example, is anyone passing anyone else? Who's running faster? Who's going slower? And you might find your graphs to be helpful. So we have graphs for each of the tortoise and the hare. But let's make a little chart where we're gonna, for each animal, we're gonna say what their location is and what their speed is at time t equals 1. Okay, so at time t equals 1, we know that the tortoise and the hare have both gone 4.5 miles, okay? The tortoise has just gotten there, whereas the hare has been sitting there for quite a while having tea. Okay, so they're both at 4.5 miles. And the rhinoceros we can calculate their location by plugging a 1 into this formula that tells us their distance. So if I plug in a 1 here, I get 4.5. 4.5 miles. So they're neck and neck, right? At t equals 1, they are tied. Okay, they are all at the exact same location. But who is running fastest, right? Is anybody running faster or slowing down? Okay. So their speed at t equals 1, we already answered for each of the animals in the previous questions. So the tortoise is going 4.5 miles per hour because they are always going 4.5 miles per hour. The hare is not moving, 0 miles per hour. And the rhinoceros is going approximately 9 miles per hour. Okay. So we can say at t equals 1, all three are tied, but the tortoise and the rhinoceros are both passing the hare, with the rhinoceros taking the lead. So let's see. They're all tied at t equals 1, with the rhinoceros taking the lead. So everything that we've done with velocities today, where we did change in distance over change in time to get either velocity or average velocity or instantaneous velocity, can be also be applied to an arbitrary function that does not necessarily represent distance and time. So for a general function, instead of saying average velocity, we say average rate of change. And instead of instantaneous velocity, that becomes instantaneous rate of change. Thus, the instantaneous rate of change of a function y equals f of t at t equals a is the same definition as the instantaneous velocity definition. It's just rate, now we just call it rate of change. So we take the average rate of change from a to a plus h, and then we take the limit as h goes to 0. Okay, and this image, this diagram is exactly why that formula is what it is. So we have a fixed point at a comma f of a, and a varying point at a plus h comma f of a plus h, where a is just some amount of time after t equals a. So if t equals a, you add h to it, you get t equals a plus h. And then we calculate the slope of the secant line connecting those 2 points. And then we take the limit as h goes to 0. So as the varying point approaches the fixed point, and when the limit goes to 0, those 2 points merge, and you have the instantaneous velocity, which is the slope of the tangent line at x equals a, or t equals a. The instantaneous rate of change of a function at t equals a or x equals a is called the derivative of the function at x equals a, and we denote it with this little apostrophe, okay, and we read that f prime of a. The derivative of f at a is this limit. It's the slope of the tangent line. To summarize, our most important definition of the entire semester is the derivative of f at x equals a, also known as the instantaneous rate of change at x equals a. It is the slope of the line tangent to f at x equals a. Just a little more vocabulary. Finding the derivative of a function is known as differentiating the function. And if a function has a derivative, the function is called differentiable. And we're going to talk about a little bit more about both of those things later in chapter 2. Okay, our next statement is super important. The derivative of a function at a point is the slope of the tangent line of the function at that point. So we'll do a call and response. So I'm going to read the unbold part, and you, sitting at your computer, are going to read the bold part. Okay. Here's the Cliff Notes version. The derivative is the slope of the tangent line. In case you missed it, the derivative is the slope of the tangent line. And one more time with feeling, the derivative is the slope of the tangent line. Given the following data for the processing speed in megahertz as a function of circuit density in, I don't know what those units are, megabytes per millimeter squared, approximate the instantaneous rate of change of processing speed when the circuit has density 6 MB per mm squared. Okay, so we want to approximate instantaneous rate of change. So let's just underline what they want us to do here. Okay, so instantaneous rate of change at 6. Okay, so I would like to know how fast this function is changing when little d equals 6. Okay, so that means I would like to find the derivative at 6. So S is the name of the function. So my inputs are little d, my outputs are capital S. So what I really want is S prime of 6, the derivative or the slope of the tangent line when d equals 6. So the definition of that would be the limit as h goes to 0 of s of 6 plus h minus s of 6 all over h. Unfortunately, I can't make h go to 0 if I don't have a formula, right? I can't calculate this limit without a formula. So all I can do is estimate this limit using an average rate of change with the smallest interval I can. So the smallest interval I have available is 6 to 7. That's the best I could do. Okay. So I'm going to say this is approximately equal to s of 6 plus 1 minus s of 6 over 1, where I'm just letting h be 1 because that's the smallest I can make h given the data I have. Okay, so the best way to approximate an instantaneous rate of change is with an average rate of change over a small interval. The smallest interval I have available to me with this data is 1, to go from 6 to 7, an interval of 1. Okay, so I keep working on this. So this is going to be s of 7 minus s of 6 over 1. S of 7 from the table is 725. S of 6 from the table is 1075 all over 1, and that comes out to negative 350. And my units are going to be S units, right, over D units. Okay, S units over D units. So that would be my S units are megahertz. I assume that's what MHz means. I don't know. Over, and then the D units were MB per mm squared. This is your second activity for this lecture, for this lesson. So I want you to take a few minutes to try to work through this on your own. Pause the video while you do that. And then when you're done, you can come back and watch to confirm your results or to clear up any confusion. Okay, go ahead and pause your video now. Okay, so now that you've taken a few minutes to try this on your own, let's go through it together. You're working in the analysis department of a large company and you want to study the effect production value P of an ad campaign has on its customer approval rating, A. After interviewing a series of focus groups, you have the following table of data. So production, some various production values associated with customer approval ratings. Assume that A of P gives the customer approval percentage as a function of the production value P. Estimate A prime of 3,500. And let's see, so that would be the instantaneous rate of change when production value is $3,500. So let's just highlight what they're asking. So they want to know when we spend $3,500 on an ad campaign, okay, we get 62% customer approval rating. But what I would like to know is the rate of change. So what is my rate of return if I spend another dollar? How many more percentage points can I expect to get? Okay, so my instantaneous rate of change would be A prime, oops, A prime of 3,500. Okay, my instantaneous rate of change at 3,500. And remember, that is the limit as h goes to 0 of A of 3,500 plus h minus A of 3,500 all over h. But I don't have a formula to use to actually take this limit. So the best I can do is approximate this limit using as small a value of h as possible. Okay, so I could use um, the interval from $3,500 to $4,000, or I could use 3,100 to 3,500. Okay, so I want to use the smallest h possible, so I'll probably use the 3,100. Um, But there is no right or wrong answer here. They're both estimates and both valid. Okay, so I think maybe I will use my H to be 500. Okay, so 3,500 to 4,000. So we're going to say this is approximately equal to A of 4,000 minus A of 3,500 all over my change um, in H, or sorry, my change in production value, which is $500. And that comes out to 67 over 62, sorry, 67 minus 62 over 500, which is 5 over 500, which is 1 over 100. And what are my units on this calculation? So they are going to be percent, right? Customer approval units over production value units. So this is going to be percent per dollar. So 1/100th of a percent per dollar. Okay. So for every additional dollar spent, we can expect to increase approval rating by approximately 1/100th of a percent. Okay, again, we just answered this question. So what are the units on A prime of P? So our calculation was 67 minus 62 over 4,000 minus 3,500, right? And the 67 and the 62, those were percentages, percent, and this was $4,000 minus $3,500. So that came out to 1 over 100, and my units are percent per dollar. So we could think of that one as 1% for every $100 spent, or 1/100th of a percent for every dollar spent. Okay, interpret your answer in real terms. Okay, so we know that A prime of 3,500, we just calculated, is approximately 0.01% per dollar. Okay, so when P production value is $3,500, increasing production value by $1 causes approval to increase by approximately 0.01%. Okay, so here's the data again. The company asks you for the most cost-effective budget for the campaign. What production value for the ad campaign would you recommend for the company? How much should they spend on their ads? Okay, discuss what cost-effective means, or think about what cost-effective means. There are multiple ways to answer this question. I think a commonly used term in business and lots of other areas um, is diminishing returns, right? So if you spend an additional dollar and that will get you 5 extra approval points, that's a dollar well spent. But if you spend an additional dollar and it only gets you an approval point, that's maybe a less well spent dollar. Okay, so what we could do is we could calculate the average rate of change between all of each set of subsequent data points, um, and figure out when do we hit diminishing returns? When does an additional dollar not get us as much? So I'm going to go ahead and do all of those off camera, and then they'll just pop up in a second. All right, so I calculated the average rate of change for each interval here. So this very first interval where we went from 35% to 37% over a $1,000 jump in spending, that comes out to an additional 0.002%, so 2 thousandths of a percent for each additional dollar spent. Okay, and then my next interval, spending additional money increases, we have increasing returns. Each additional dollar spent yields a 15 thousandths of a percent increase in approval rating. Okay, and then it jumps to 0.02%, and then 0.05% for each additional dollar spent. Okay, but then we go to 1/100%, 1/100% of 1/100%. So it depends on what you're looking for, right? If your goal is just to get the largest customer approval rating possible, then right, you would go with the largest production value. But if you want to get the most value for your money, um, I might stop after we get this big 5% jump. So we get the most bang for our buck going from 3,000 to $3,100 in production value. Um, I would maybe spend 3,200, right? Because you can expect that you'll get another 0.5% for another dollar spent. Okay. So maybe a little bit more than 3,100, but I wouldn't go all the way to 3,500 because we're getting diminishing returns. So I would spend between 3,100 and $3,500. But again, there are lots of ways to think about this question, and there is no one right answer.